This video is for Unit 5, Lab A, Balancing Equations Using Molecular Models. In this lab, you're going to be sketching out the reactions on the lab using models for each molecule that's present in the reaction. In order to do this, you're going to need some different colors to represent elements in the reaction and to build the molecules and show the numbers of molecules that are present in each reaction. An alternative to this, if you don't have colored pencils, is just to use different shapes for each element in the reaction. Or if you want to take it a step further and actually use specific objects, food items or other objects, to represent each element and physically build the model for each of the molecules, that's a possibility. We're going to look at 4 scenarios of different types of molecules that you might encounter in the activity. The first is a binary molecule, that which contains only 2 elements in the formula. The other are non-binary, that contain more than 2 elements in a formula. Some non-binary formulas are written without parentheses. Other times, non-binary formulas will have parentheses. The last thing that we'll look at is coefficients that you've added to the equation to balance the reaction and what the coefficient indicates about the number of molecules. You'll recognize a binary formula because you'll only see 2 elements written in the formula, and a binary formula will never contain parentheses. These can come in either an ionic or covalent form, but for this activity we can draw each of these molecules the same way whether it's ionic or covalent. First thing you need to do is identify each element in the formula, and we're just going to choose a color to represent each of those elements. In this case we see sodium in the formula, which I'll be using red, and we see chlorine in the formula, which I'll be representing with green. And the formula shows that there's only 1 sodium and 1 chlorine in the formula. And so we can just build this model by attaching 1 sodium atom to 1 chlorine atom. Now I'm always going to show that these 2 things are connected as a molecule by connecting the objects that I've drawn with a bond that can just be represented by a solid black line. And so this model represents 1 sodium atom connected to 1 chlorine atom, creating a sodium chloride molecule. We could do the same for carbon dioxide, where we have 1 carbon molecule or 1 carbon element. I'll use purple, and oxygen, which I'm going to represent with orange, except in this case we do have the subscript 2 indicating that we need 2 oxygen elements. So this model represents a carbon dioxide molecule with 1 carbon connected to 2 oxygens in the formula. When a molecule is non-binary, it'll always contain a polyatomic ion. In some cases, the formulas will have parentheses around the polyatomic ion, and in some situations there won't. However, in both instances, you do want to identify in the formula where the polyatomic ion is located. For example, in ammonium chloride, the NH4 ammonium is the polyatomic ion, and in potassium sulfate, SO4 is a polyatomic ion. And even though we're going to use a different color for every element in the formula, the first thing we want to do is build the polyatomic ions and attach them to the other individual atoms. So in the case of ammonium chloride, I'm going to use purple for the nitrogen, green for the hydrogen, and orange for the chlorine. I'm going to start by building the polyatomic ion ammonium, the NH4, which says that I need one nitrogen atom connected to 4 hydrogens. And that ammonium is connected itself to the chloride ion. So the model is representing 1 ammonium connected to 1 chlorine and building the molecule ammonium chloride. We could do the same thing for potassium sulfate. For potassium sulfate, I'm going to use red for the potassium, green for the sulfur, and blue for the oxygen. Again, I'm going to start by building the polyatomic ion, which has a sulfur connected to 4 oxygens. And that sulfate is then connected to 2 potassium ions. So my 2 potassium ions are bound to the sulfate, giving me potassium sulfate K2SO4. At times you'll find a non-binary formula that has parentheses. In the example of calcium hydroxide, we're going to do this similar to how we did other non-binary formulas, taking into account the subscript outside of the parentheses. So once again, I'm going to locate my polyatomic ion. The hydroxide in parentheses is the polyatomic ion, and pick a color for each of the oxygen and hydrogen atoms. In this case, I'll use blue for oxygen and purple for hydrogen. And like we did before, we're going to start by building that polyatomic ion with 1 oxygen and 1 hydrogen in the formula. So this is a hydroxide ion. However, in this formula, the subscript outside of the parentheses is telling us that instead of just having 1 of the hydroxide ions, we have 2 of those. And so I'm going to draw my molecule hydroxide twice. So I've drawn 2 of the hydroxide ions. And again, the formula indicates that this is attached to a calcium ion. Calcium I'm going to represent with an orange color. So this orange calcium is then connected to those 2 hydroxide ions. The last thing we'll look at is what the coefficients that you've added to an equation do to the models. So when you're balancing an equation, you add coefficients to the front of each formula to indicate how many molecules of that formula are present in the reaction. So in this case, if we've added a 2 in front of the formula NaCl, and we want to represent that with a model, essentially the coefficient, indicates that we're going to build this model NaCl like we did before, except we're going to build it 2 times. So like before, I used red for sodium and green for chlorine. I'm going to build this sodium chloride molecule. But the coefficient 2 in front of the formula indicates that I need to build that model twice. So this model represents 2 of my sodium chlorine molecules. Important thing to remember is that the coefficient is telling you how many of the models to build, but each of those models is separate of each other and not connected together. So instead of having all 4 of these objects connected as one object, the coefficient just represents that there's 2 individual models of the same object. We can do the same thing for calcium hydroxide, where the coefficient 3 has been put in front. So I'm going to rebuild my calcium hydroxide, except rather than just building it once, the coefficient says that I need to build it 3 times. So the model is representing 3 molecules of a calcium hydroxide. So for Lab A, this is what you're going to be doing. For each of the reactions in Lab A, you're going to balance the equation. Once you've balanced the equation, you'll use the formulas and coefficients in the equation to sketch a complete model for that reaction. Once you've sketched your models, you should also identify the type of reaction for each of the reactions, as we've done on previous assignments. Finally, once you have all the reactions balanced, sketched, and identified, you can take a photograph of Lab A and attach that into your Google Classroom when you submit it.